Welcome to the 5th episode of The F-Team. The F-Team is a fortnightly podcast brought to you by the team at Fast Track Technology. I'm your host, Hayden Van Roon. In today's episode, we explore how fragile the internet can really be, and we take learnings from the Bureau of Meteorology's recent data center upgrade. Let's get into it. I'd like to welcome back our team leader of connectivity, Bilal Chisti. Welcome back, mate. How are you?
Thank you. You didn't have me the last time around, so I thought, can't have two podcasts without me on it.
Yes, no, that would be such a shame. A belated happy birthday, by the way.
Thank you. I've joined the 31 club. Actually, I checked. There are 5 team members in our company who are now currently 31.
Oh, really?
Yeah.
I didn't know that. I'm one of them. Did you count me? Yeah.
Yep.
Okay, good. There you go. Wow, we're getting older. This team of ours. It's good.
Yeah.
Very good. Well, I'm glad you're on because I wanted to get your insight into a couple of things that have happened recently. And they're pretty meaningful, particularly around the area of business networking. And I thought you're the man to get on to chat to me about that one. So let's get into it. So the thing I wanted to get you in to talk about is BGP hijacking. So we've witnessed some pretty significant BGP hijacking incidents in recent times. So one of the famous incidents caused YouTube to be unreachable by any user for about a 2-hour period back in 2008. And there's been some recent incidents that have driven us to want to talk about that. But I wanted to start by asking you to share. There'll be some people who know what BGP is, but for those who don't, Bilal, what is BGP and why is it so important in the context of the internet?
So BGP basically stands for Border Gateway Protocol, and it's one of the most core routing protocols which is used for the internet. It's probably one of the major protocols used for dynamic routing, especially upstream, and the core of the internet basically depends upon it. The old way of doing it, really old, was static routing. So you have, traffic from here will always go from here. Dynamic means depending upon which person is advertising a specific prefix, the traffic will either go to one particular place or somewhere else, allows for failover and such. So a cornerstone of the public internet.
There you go. So you can imagine that if someone was be able to harness or tap into that dynamic routing, that they could cause some havoc. So what is BGP hijacking and what does it usually entail?
So the way the BGP networks are set up all across the world is basically on a trust basis. So you're trusting that the other person, that's basically the old school way of doing it. You're trusting that the other person is advertising the correct ones, so that it allows seamless interaction between all different networks. The issue is if someone starts doing something which they should not be doing. So if advertising prefixes which they do not own, or either accidentally or for malicious purposes, and then it can cause havoc. BGP hijacking basically means you're advertising someone else's prefix, either accidentally or maliciously. And then, so when you advertise a prefix, suddenly all traffic going toward that prefix will start coming towards you. So, and if you don't have the resources to back that, they'll just get dropped.
So it's pretty big deal, and you can imagine that when someone starts doing that, either inadvertently or deliberately, it can cause some pretty big havoc on the internet, right? So as I understand it, in the YouTube BGP hijacking incident, the video sharing website had its prefixes stolen by actually Pakistan's national telecommunications company. So that they're called PTCL. I don't know what that stands for.
Yes.
But the telecommunications company was responding to a directive from the government, from Pakistan's government, to block and censor YouTube from Pakistani users. And in the process, they inadvertently blocked all global users from accessing the video sharing site. So, Bilal, obviously, we've talked a bit about what it is, but what were the specifics around what happened with PTCL and how did they even make such a big mistake, being, I believe, they're Pakistan's biggest telecommunications provider? So you'd assume they know what they're doing.
Yes, so they're Pakistan's version of Telstra, essentially. So yes, the big dogs. So in essence, what happened was they got a directive from the government for whatever particular reason to block YouTube traffic. Now, to block a particular website, there's multiple ways of going about it. They just went about the easiest possible way, which is okay. We'll take all traffic going towards YouTube, take it towards us, and then throw it into a black hole, and it'll never see the light of day. Now, the issue with that is you need to be very careful on what effects it has on the wider network. So they implemented this rule. So every traffic in Pakistan is going towards PTCL and going into a black hole. The problem that probably one network engineer that had in this case was he forgot to filter it on the upstream provider. So not only were they advertising that towards the local Pakistan community, it was also being advertised upstream via their provider, which I believe is PCCW, which is the Hong Kong-based transit provider. And once they got it, they forwarded it on because they're trusting that if Pakistan is advertising, if PTCL is advertising this one, they're probably right, and they advertise this further on to the network. And then that just has a massive follow-on effect. So within a couple of minutes, most of the world's internet had YouTube's prefixes pointing towards Pakistan. So all traffic went to Pakistan and then into a black hole.
So it's interesting. So the thing I picked up there was that the Hong Kong-based IP transit provider just trusted that it was right.
Yeah.
So why is that inherent level of trust there, and why do an upstream provider just say, okay, if another provider says it's right, then it must be? How does that work?
Well, there are a few different things that providers do to overcome this. So a lot of cases, so for example, if we're advertising a prefix to our upstream provider, filters. So we tell them beforehand, okay, by the way, we'll be advertising this, only allow this. The old school way of doing things was, okay, you have an IP prefix, you go to the internet registry, you register it according to your name and your AS number, which is your autonomous system number, and that will act like, okay, so a sort of proof of ownership. The issue with that is there's no automatic way of actually verifying that. And a lot of upstream providers, when they're communicating with other tier 1 providers or other tier 2 providers, they sometimes forgo that one just so that it reduces the level of complexity. And in this case, that's what happened. PCCW got that advertisement from PTCL, not from a smaller provider in Pakistan. They assumed, okay, there's a level of trust here. They've never done this before.
Yeah, the big dogs, they know what they're doing. Yeah.
Yeah. And then it just spreads.
Interesting. So, is there much that YouTube in this scenario can do to actually mitigate this change, or is it really up to the PTCL to identify, hey, I made a mistake and make the change?
Bit of column A, bit of column B. So the way the internet routing works is you can advertise prefixes, but there's different sizes. So any router, when it's trying to pick which route to go, it takes a more specific route. So whichever one is more specific, that path is taken. So PTCL initially, I think, advertised YouTube /22, which is like a larger prefix. The same as what YouTube was advertising as well. So suddenly there's two different prefixes. Either traffic will go towards this one or this one. If it goes towards this one, this goes into black hole. YouTube, to counteract this, advertise the prefix in /24s, so that's more specific, and try and get traffic back in. But unless PTCL removes that /22, there's always be an issue of another person advertising there and possibility of some traffic heading up there in case, say, YouTube stopped doing it. So yeah, bit of column A, bit of column B. They can have some stuff which can help prevent this, but they also need this other person to stop doing what they're doing.
So it really says something about the way, these providers work, right? There's a lot of trust, there's a lot of codependency, and it kind of highlights the fragility of the internet as we know it today, right?
Yep. Something similar happened a few weeks ago. We talked about in a previous podcast about a different provider in the US when they had a massive outage. In that case, that wasn't a case of BGP hijacking, but what happened was internally they messed up and they couldn't route traffic in. So traffic, they were still advertising prefixes, but they have no way of rerouting the traffic elsewhere. So that's not BGP hijacking, but that's another way, like traffic is coming towards one provider and then they have no way of handing it off to somewhere else, to the relevant party, and it just gets dropped.
Yeah.
And suddenly it causes massive outages.
It's crazy.
And yeah, and this can't really be predicted as well, like when this will happen. So
there's just a degree of user error, right? That
yeah.
And the reason why, this is obviously the YouTube incident is quite an old incident, but I think it highlights that this issue's been around for a while, and there's still incidents of BGP hijacking happening today, and the story is quite similar, and that's kind of why I raised YouTube, right? Because we had another incident from another telecoms provider. It's much closer to home. In September of this year, Telstra accidentally hijacked approximately 500 of the IPv4 prefixes, causing an increase in web latency around the world. So I'm keen to get your understanding of what happened here.
Something similar. So again, it was a user error. It was technical error. So someone at Telstra accidentally advertised prefixes which they were not supposed to advertise, which were not owned by Telstra or any of their customers. So what happens in this case, they advertise a prefix which is not owned by a customer. Traffic for that customer ends up at Telstra, and because they don't have a connection to that customer, it just gets dropped. So, and it causes an outage, and initially it's very difficult to notice as well, because that particular customer, which could be any company, in this case, there's a mailing company, Proton Mail and a few others, they look internally, they say, okay, all of our services are working perfectly. Our connection to our upstream providers is working perfectly. They say they don't have any issues, like where is the issue? And when you then try tracing the traffic, it suddenly is going to Telstra, and they're like, wait, we don't buy services from Telstra.
So that's right. So that was one thing I noticed, is that Telstra made this change, and one of the organizations, as you mentioned, that was most affected was this Swiss-based email provider, Proton Mail. So you sort of touched on them. What were the impacts the organizations that felt the impact? What were the issues that they're actually experiencing as a result of Telstra's error?
So they can either have complete outages in some cases or partial outages. So
Right.
if two carriers are advertising the same prefix and of the same specificity, some traffic will end up here, some traffic will end up here. The traffic which will end up at Telstra goes nowhere. So any person who's going there won't be able to access that particular service. Any user who is going down to the correct carrier, they can access the service. In some cases, if depending upon the way the internet is working, most of the traffic might end up at Telstra, and so most of the services might go online. So the disruption really changes depending upon how that particular customer and how their upstream transit is set up. Like how many different places are they advertising their prefixes?
Yeah.
For a smaller one, they're probably only advertising via one upstream carrier. For them, it'll be larger. So other people who have multiple different advertisements, they might not be as affected.
Yeah, there's the importance of having that redundancy in your network, right?
Yeah.
And so, how did guys like Proton Mail, what did they actually do to remediate and then eventually solve the problem?
Well, in this case, so because they're smaller companies, unlike YouTube, which has obviously very close ties to tier 1 providers, and they can very rapidly change what they're advertising to the internet or to different carriers, these guys can't. So they're basically dependent on Telstra to stop advertising their prefixes. Similar to YouTube, if they're advertising larger prefixes, they can ask their upstream providers to do more specific ones and try and get it back. But they're mostly dependent on Telstra to stop it. Unlike a larger company which has more closer ties, or if it's a different ISP who has a more direct control of the advertisements, they can make the changes on the fly. But a person who's buying through someone else doesn't.
Pretty crazy. And when you say that you have to these providers are getting in contact with each other, I imagine it's as simple as actually getting on the phone and sending emails and navigating each other's organization until you find the right person who's who, you know, like, oh, actually, I changed something, I did something wrong, right? Like it's not as, you know, it's not more complicated than that, right? The way they communicate. Is that fair to say?
Basically, yes. So most of these are like ISPs, similar to us. They have a network operations center.
Yeah.
So whenever an issue like this happens, you simply just call the NOC and
Yeah.
hope you get a person online who can solve it as quickly as possible.
Yeah. It's pretty important. And I think, you know, like I touched on before, the reason why we're talking about this is that it really highlights, and you'd think there might have been some shift between, say, the incident in 2018 versus 2008 versus 2020, but the way in which the problems are being identified and solved seem to be very much the same. So, you know, in that, you know, 12-year period, we've really seen very little shift in the way that these incidents are recognized and handled. And there's things that we can talk about in a sec that you can do to prevent it. But in terms of actually identifying these challenges and then remediating, it's very much about how quickly you can communicate with each other. And the dependency on each other still seems to be very, very high. And if you don't have diverse, you know, upstream providers that you're peering with in your network, then you really don't have a lot of options except for yelling at the other provider and saying, "Hey, fix," because it's breaking us, right? It really highlights the fragility of the internet, right?
Exactly, yeah. So depending on how much control you have, which especially like when you're even a smaller organization, even some larger organizations, you're basically connecting to one upstream provider who's probably connecting to other ones. And if they're the ones making the mistakes, there's not that much you can do. If you have multiple ones, you can turn off one connection and hope that stops the advertisement. But there's still so much you can do. Obviously, over the past few years, even more than that, there have been other technologies, which I think we'll be talking about soon, which have been implemented to try and prevent this from happening.
Yeah. Well, let's talk about that now then. It's a good segue. So one of the things we highlighted was that resource public key infrastructure, or RPKI, is one of the technologies that organizations are using to protect against BGP hijacking. And it's fast becoming a standard across industry. So as an uninitiated non-network person, the way I was interpreting it was that RPKI has been built to replace the Internet Routing Register, the IRR, which is the previous standard that was developed to help prevent and control the availability of IP prefixes, right? So, Bilal, I think it might be worth touching on what is RPKI and how is it different to IRR?
Yes. First of all, I don't think it's designed to sort of replace it. They'll be sitting side by side because they'll be doing slightly different things. So IRR, the Internet Routing Register, is the standard way of doing things. So basically, you have a registry. So whenever you have an IP prefix, you're going to a routing registry and you're buying the prefixes from them, and then you register from them. So when you're registering, you give them all details. So this prefix belongs to this company. This is their autonomous system number. This, in case something happens, these are the contact email addresses and the name of the people or the departments where you need to go to. So if you see, okay, if you're doing a trace out and say, okay, there's in the network, this IP is causing issues, you can search on that IP and you can get all the relevant information regarding who owns that and how to contact them. But there aren't really many things which are set to use that as a source of verification. That's where RPKI comes in. So unlike the IRR, these create certain certificates tied to your prefix, and then you can use either upstream providers or you can use those as a means of verification. So an upstream provider, suppose, and we are the downstream one in this case, and we're advertising a certain prefix to them, they'll do a verification. Okay, they'll query a database. Okay, these guys are advertising this prefix. Are they even this? Is the autonomous system tied to this one? If it is, okay, let it through. Otherwise, reject this advertisement. And then the carrier can go back and say, by the way, we rejected this one. These are the ones which are failing. These are the reasons why they're failing. And either if it's an IPO owned by you, either update the records or prove that it's owned by you in whatever way. And whereas the current system is you accept the advertisement, and after an issue happens, then you go back. So the incident has already occurred.
Yeah.
This tries to prevent that from happening in the first place.
Yeah. Nice. And so I'm interested to find out what happens to the traffic when it's blocked. Does it dynamically find a new path to get to that?
Yes, in this case, they do not. So it's a case of incoming advertisements. So they don't accept the advertisement at all. So they won't advertise it on their end. So no traffic for that prefix will end up
advertised.
there.
Yeah, got it. That makes sense. Okay, cool. So my understanding, and again, is very limited, but for RPKI to really be effective, long-term, broad scale, is that it actually needs to be adopted by almost all, if not all, ISPs globally or upstream providers globally. Is that right? How does that work?
In a way, yes. So if you have two providers and one does RPKI verification, one does not, you can always make that mistake. So traffic will come down that path, they take it. So there's still a possibility of an outage.
Yeah,
And in that case, a lot of times it makes it even more difficult to try and troubleshoot. The other issue is generally with internet protocols, which we've seen with IPv6, the industry is very slow on uptaking newer protocols just because it requires time and effort.
Yeah.
So a lot of people are like, if something's not broke, let's not fix it. Yeah, because it'll require time, it'll require re-architecture, it might require you to have the proper sets and then maintaining those records. But I can see a change. For example, in the last year or so, especially carriers which we work in Europe, they come back to us and say, okay, like after this date, we'll be increasing our security and we'll be requiring RPKI after so and so days, and thereby forcing a lot of users and other carriers to uptake it. But again, that changes by region to region. But over the last 1 or 2 years, I can definitely see a massive uptake. Basically, because there's two different ways of doing it. So a lot of the internet registries, they've seen how people are slow on the uptake. So they're providing resources inside their own portals to deploy this in a very rapid and easy manner. Just trying to reduce the cost of entry, the barrier of entry, so that more and more people come in. And hopefully that'll start the flow. And once this sort of becomes like an accepted industry standard, more people will start following it.
Yeah. Interesting. Just going back to what you were saying before, it sounds like, the challenge is that having it, these prefixes seem to be like almost like a virus, right? Like you can, if you quarantine everyone, but there's still one guy out there sending out dodgy ones, and there's another provider ready to receive them, then the virus spreads. But if you got everyone who've been inoculated, or have put in RPKI in place, you're able to contain it because there's less people out there, or less organizations out there kind of spreading those incorrect destinations. So
yeah, because like we've always been, the issues that we've talked about in this podcast are mostly accidental ones.
Yeah.
There's that second vector, which is malicious. So you can have other barriers in place which will prevent certain accidental ones. But what if the other person has a malicious intent? So you're like, oh, this AS number is not advertising the incorrect prefix. Let's drop it. What if the other person is aware of that and they spoof the AS number to be that one, and they can bypass that particular one? So those are things which come into play, and that's why like they need automated like well-oiled system to prevent those use cases as well.
It's pretty scary that this sort of thing exists, and sounds like if there's a vector exploit, someone's going to invest time and energy into it. So
even governments do it.
Yeah.
That's how like a lot of governments basically read in or like get in touch. So if it, primarily I think China and the US as well. So when they're trying to basically can't get the right word, basically hijack, right? Essentially, they're not really trying to redirect traffic. They're trying to see what the traffic is for security purposes, for like intelligence purposes. So so the more the verification happens, we actually uplift our security level, and we can prevent those sort of cases from happening as well.
Yeah.
Yeah, there's a lot more happening, and there's a lot more at play than people realize.
Yeah, I think there's probably more at play than we can cover in this podcast as
Yeah.
well. I think that's a good place to wrap up. Look, I think that was a really interesting discussion. Thanks for your time on that one, Bilal. I think the internet is a much more complex place, and I think the learnings for me is that there's still a lot of dependency on trust and people working together, and there's the opportunity for things to be exploited. But I think certainly if we keep on top of it and we're aware of the vectors of attack, then we can prevent against them, right? So I think that's the key learnings for me. But yeah, thanks so much for your time, Bilal, and hopefully we'll get you on again in another couple of weeks. I'd like to welcome my next guest. He's my favorite systems engineer. Welcome, Nathan Kettle. Welcome back, mate.
No worries, mate. Thanks for having me. I'm keen to come on and talk about some more compute hardware. It's the good stuff.
Yeah, exactly. It's good to have you back. Can't keep you away. So let's just get straight into it, because we've got lots to get into today. In recent data center news, the Australian Bureau of Meteorology, BoM for short, announced they have finally decommissioned their 46-year-old data center. So this is a 1,520 square meter purpose-designed computer room, and it was first commissioned in 1974. So that kind of gives you some hints onto how old this thing is. So it previously housed the Bureau's most important operational computer systems, including those for meteorological modeling, and it was thought to be valued around 60 million in about 2003. So the decommission is part of an ongoing multi-year IT transformation project. The BoM noted the reason behind the decommissioning was to remove vulnerable systems and migrate to a modern architecture. And the last part of that, my friend, is why I brought you on to chat to us today. So the remove vulnerable systems part of that statement is most certainly referencing the infrastructure that was targeted in the cyber attack of 2015 that BoM felt back then. So the perpetrators of this attack were thought to be a foreign intelligence agent, or a series of agents from an unspecified country, China. They successfully gained access to some confidential government data via a remote access tool and a crypto locker ransomware, which exploited the vulnerabilities of its aging infrastructure. So over the past 5 years, BoM has invested heavily in consolidating and reducing the complexity of its systems and infrastructure. So Ned, this is why we're here today. The first thing I wanted to ask you, what outside of the obvious can you tell us about the risks of running out of date hardware for an extended period of time?
Sure, mate, sure. So to start off, I'd like to highlight the risks of saying BoM so many times in a video and getting it blanked out on YouTube. And also
whispering China.
And also creating an international incident with our main trading partner. So congratulations, we've achieved a lot more than we expected to achieve already. But obviously the main issue in this case is security. There are other factors, of course, but the fact that our sensitive government data is or was at least open to exploitation is a major concern. This is something that sort of really wasn't too front of stack in a lot of people's minds before probably January 2018, when obviously the highly publicized vulnerabilities like Spectre and Meltdown first came to our attention, highlighting a lot of the ways that malicious agents, should you say, that aren't our trading partners, can access systems that are older. without that. They don't have the hardware sort of mitigations built into them that modern hardware has. And it's not just two vulnerabilities that popped up a couple of years ago that's been causing headaches. Every week, every month, researchers are finding more and more vulnerabilities that hit systems in different ways. There's currently a lot of research that goes into it. From accessing through CPU kernel leaks and memory leaks and all sorts of different vectors. So it's not just software, it's not just network, it's right down to the hardware that things run on that we need to look at security from. All of the major chip makers, Intel, AMD, and ARM, so basically whichever platform you're running on, have vulnerabilities to some extent. Obviously, some are less vulnerable than others. The main vector of attack is against Intel systems, and this can be because there's so many of them. It doesn't make too much sense to sort of focus time breaking into targets that aren't too prevalent out there in the wild, but they do seem to suffer from a lot of the issues and sort of having the hardest time mitigating against these vulnerabilities. So older Intel-based systems can be particularly vulnerable. And then again, so can AMD and ARM systems as well. But there's just varying factors that sort of scale the severity in that situation. So from a government or high-value target perspective, if you're a corporation, a large corporation, even small, medium business sort of can start thinking about these things. But specifically large targets, obvious targets, need to consider the age of their hardware when they're looking at their security approach. And it's not just security either. We talk about that as the main one because that was the impetus behind the change. But old compute hardware, I don't know if you've ever had an old computer before, but they tend to break. They're not the most reliable things in the world, especially when they've been working for any number of years, decades, potentially. So there's maintenance headaches, increased downtime, which is also increased cost. There's also when a component fails, it just increases the amount of work you have to do to source a new one, replace it. It takes people's time and effort away from the day-to-day running. So there's all sorts of things to do there with maintenance and reliability. They're also less efficient than modern systems. So performance per watt is a thing. So you could possibly replace
at scale, right? Like when you're talking as you grow and scale, those little measurements, they add up, right?
Exactly. So there's a lot of different cases we could use here, then depending on the application you're using. But for instance, NVIDIA's DGX2 is a small box, takes up about 5 RU, but for AI and inference learning, it can replace an entire rack. Or cabinet of racks in some cases of older hardware and do the same or more work for 1/20th of the power bill. So modern hardware and modern approaches to solving problems is usually a lot more efficient. So there's savings to be had there. And on the monetary side as well, depending on obviously how your organization works, older hardware obviously has done its depreciation. So there's no tax concessions on those. So it could be actually worth your while upgrading your old hardware and being able to depreciate some of that against your bottom line. So there's quite a few considerations to upgrading old hardware.
That's right. It's always good to have a security breach. Not really, but it tends to be that there has to be some big bang event like a security breach to move on some of these large organizations to actually make the investment. And it's a bit of a shame that it takes a huge breach of potentially, especially when it's government, our data. I'm not sure how much our data was at the BoM, but to make them move. And I think, as you say, a lot of the things you raise are just common sense in a lot of ways, right? But yeah, it is a bit of a shame that it does take that big bang event to move us along.
It's not an insignificant investment. That's where the problem comes in. You need to have that. that force that can actually push an organization into spending that sort of investment. And sometimes that doesn't happen until after the fact. Unless you're in a position to proactively respond, then so yeah, it can be a little difficult to do sometimes.
I'm getting the feeling like it's changing though. IT is moving away, as it has been for the past probably 20 years, that view of being the cost center that you just have to have it to make it work. And as long as you get the bare minimum, then that's fine. I think we're very much moving away from that mentality and looking at being what can we do? How can we improve our business by investing in technology that's actually going to help us do better? And I think to all the points you mentioned there, some of them are operational and just getting your costs down and consolidating everything, and others are about, okay, what can we actually achieve with this additional compute? And that leads me on to my kind of next point that I noticed when looking at the BoM announcement, where they're investing big time and into creating a compute environment that actually allows them to do more, while obviously attending to those security risks that they fell victim to, right? So the BoM have named their shiny new data center that they've replaced. So it was that old thing that we're talking about that was first commissioned in 1974. That was Australis 1. So the new data center is called Australis 2. And if a cursory look at the specs, and put my hand up, I'm not a spec guy, but what I did notice is that they're doing something fairly unique, at least to my untrained ears and eyes, right? So BoM have deployed a series of supercomputers, including the Cray XC50 and the Cray CS500, right? So in my understanding is the Cray XC50 supports Intel Xeon CPUs and NVIDIA Telstra P100 processors, whereas the Cray CS500 is an AMD EPYC system. So the interesting thing here is, besides doubling the compute and storage of the previous system, Australis 2 has embraced what it seems to be a mixed ecosystem approach. Now, I'm not sure if that's the right word, but this seemed to be a fairly interesting kind of approach, right? So Nathan, why do you think BoM has adopted this mixed ecosystem approach?
Without knowing their exact deployment and their exact sort of use cases for these systems, a little hard to say, but it feels like a typical supercomputing platform in the last 5 to 10 years, it was Intel. No decision to be made. That was your option. I think the fact that they've included AMD EPYC powered supercomputers sort of really highlights their security concerns, since there are fewer gateways into the AMD EPYC systems. Not only that, the AMD flaws that do exist, they're mostly, or at least a good chunk of them, are only executable if you have physical access to the machine. You have to be there with it to do it. It's not something that you can execute remotely like a lot of the other flaws. So, so from that perspective, if you want the safest platform from a security standpoint, then if you were going to have something that's going to keep all your data safe, not so much the calculations that are going on, but the actual data and the stuff that's sensitive, you'd be much better off housing that on an AMD EPYC supercomputer rather than any one of the other options. Out there in the wild, the actual ratio between Intel flaws to AMD flaws is 16-1. So they've got a lot of work to do, and they're doing it over at Intel. They're doing a power of work to try and to clean all these up, but it's like it can't happen overnight, but it will happen. It's just time, because a lot of these hardware mitigations, you have to redesign your architecture completely. So yeah, that's the state of play currently. So I would assume, well, I don't like to assume, but I have to assume at this point that would be why. Yeah, just less of a target, less flaws, and it's been rated by many other agencies that do these security researches that it's just more secure.
Cool. And the other thing that kind of popped up as a question for me on this was, are there specific workloads that benefit from having both of these kind of architectures or ecosystems embedded into the environment?
Oh, for sure. It's like anything. There are things that you can do better than I can, and maybe something that I can do better than you. We haven't figured out what that is yet, but we're going to keep looking until we find that. But so each system's architecture is developed not only differently, but you can develop it for a specific work set. It's not a world of where it's just a CPU anymore. There's all sorts of accelerators. There's all sorts of custom SoCs or system on chips. You can do just about anything with silicon these days. So if you really want something to specialize on a certain work task, then you can get that. So I think what they've done by having the sort of hardware pointed towards Intel and NVIDIA on the compute side, what that tells me is that specific hardware is designed or at least specialized in stuff like TensorFlow and fluid dynamics, which fluid dynamics is a really big calculation in weather prediction for obvious reasons. We live in a sea of air that's full of moisture, and the seas play a really big role. Precipitation and it's all fluid dynamics. So you need something that can crunch fluid dynamics really efficiently and really fast. So that sort of comes down to it too. If you really want something done efficiently, you need to specialize. It's no good having a general purpose system all around, because it's just not going to give you the results that you want. And Intel are really great at low latency workflows and strong on AVX instruction sets, which is really good for keeping GPUs fed with data. You don't want any of those very, very expensive NVIDIA GPUs to be sitting idle. You want them to be going absolutely as flat out as they can. Whereas AMD, they're really good at high CPU compute density and high memory capacity. So if you want high virtualized workloads that are really secure and somewhere safe to store all your data, AMD are really strong on encryption. They're probably the market leader when it comes to encryption. So there's all sorts of considerations in the design, and it seems that each of these two supercomputer specs, even though we don't have the exact specifics, seem to sort of play towards those roles.
Sounds like a pretty powerful machine, right? Like, and I think looking into it, I think I've read the words 4 petaflops somewhere. So
don't giggle at that. It's an actual word.
So. Like for the uninitiated, I'm sure there's quite a few listeners that consider themselves initiated. But for those who are uninitiated, are you able to put into perspective how much power these machines have compared to your normal rack setup or your PC?
Can we sum it up as stacks on stacks? It's a lot. So to actually explain what a flop is without giggling, is it's a floating point operation.
Not possible.
Right. So there we go. I've lost it. So yeah, I failed there. You're obviously better than me at that too. Cool. Yeah. So the floating point operation is just a basic calculation that a processor, whether that's a CPU or a GPU or any other type of processor, can perform. I know it's a little boring, and I hope everyone's still awake at that point. So these can be subjective. How you measure your flop is highly subjective. You can use different workflows and different instruction sets on different types of hardware to come to that calculation. So without knowing exactly what they use to come to that 4 petaflop calculation, it's kind of a little difficult to really nail down, because you can do it mathematically, but it involves a lot of numbers, letters, symbols, and brackets, which is probably a little bit beyond me and my Casio calculator on the desk here. So if we sort of try and sum it up against an average user's desktop, say from the last 2 years or so, which would be anything around probably a 6-core Intel or AMD desktop processor, in something like Geekbench 4, which any user can go and test their own computer on, by the way. You can go download that and test. An average consumer computer would be around 400 gigaflops. So I think that's 400 million flops. But in order to scale that out into petaflops, you got to add 6 zeros to that 4. So when you scale that out, it's actually 10,000 times if my maths is correct, more powerful in one cabinet that takes up about 5 or 6 rack spaces in their footprint. So yeah, it's quite a bit. But yeah, tough to compare apples to apples.
Or flops to other flops. That I don't know. Like I just can't get past that word. To be honest.
You can't tell me that electrical engineers and CPU engineers don't have a sense of humor.
Yeah. I can try, but I would be failing. So yeah, it's pretty impressive. Like half of that went over my head, but there's certainly there's a scale of measure there that is huge. And I think that's what it comes down to in the end, right? Is that it's using outdated, the power of hardware that the rate of improvement to this hardware is improving at such a scale that holding on to hardware for too long means that you just lose that scale, like the economies of scale on that performance. And
it's growing day by day. It's growing day by day because accelerator's the new buzzword in compute. There's all sorts of new magical pieces of silicon out there that can do things that you specifically want them to do many times faster than a general compute. So I know we call the CPU, but it should be more like GCPU or general compute processor, because it does general tasks very, very well. But when you want specific parallel, like massive throughput compute, that's where like the GPU comes in really handy. Massive parallel compute, huge access to memory bandwidth local to the processor on the graphics card. But it's not just that. There's other pieces to the chessboard now, like field programmable gate arrays, which are basically AMD or Intel will create silicon for you, custom to how you want it, and you can then do the programming of the microcode yourself. So if you just don't like the off-the-shelf stuff, you can basically create your own CPU, do exactly what you want. Also ASICs as well, which is application-specific integrated circuits, which are made to do specific tasks. There's any number of ways to accelerate your compute workloads.
It certainly paints hardware in a kind of different way, where we're kind of everything's moving into in public. You feel like there's been this shift to public cloud, but the change in the hardware means that it's just really attractive if you've got a specific. And I think we've touched on this in previous podcasts and webinars. It seems like when you've got really specific requirements, hardware really shines. And this is coming from someone who knows nothing what they're talking about, but that's the theme that I keep hearing coming out when I talk to you guys about this stuff, is that if you've got a problem you need solved, general computing, whether it be public cloud or general hardware, is not up to the task, and you have to look at hardware.
That's right. Yeah, bespoke solutions at that point.
Bespoke solutions. Yeah. Thanks for listening to the latest episode of the F Team. You can find us wherever you get your podcasts, and the video is available on our website, www.ftpl.com.au. See you next time.